Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about waves, and we said waves in general are the motion of a disturbance. And then we said that waves, are of two types: mechanical waves and electromagnetic waves. Mechanical waves are those type of waves that in order to travel they need a medium. So without a medium they cannot travel. But on the other hand, electromagnetic waves are those type of waves that do not need a medium. Now, mechanical waves, of course, divide into two categories, and these are longitudinal waves and transverse waves. Okay, while electromagnetic, in electromagnetic, we only have transverse waves here. Now, longitudinal, we said, when we have a longitudinal wave, the particle in a medium would vibrate parallel to the direction of wave travel. So if the wave is traveling to that direction, the particle here would only vibrate back and forth, which is parallel to the direction of wave travel. While for a transverse wave, the particles of a medium vibrate at right angle, perpendicular to the direction of wave travel. So if the wave is traveling in that direction, let's say, if that is the direction of a wave here, this particle would vibrate up and down, which is at right angle to the direction of wave travel. And then this would be the difference between the two. And of course, we draw the shape of each wave. And then today we also learned about some other properties of a wave for transverse and longitudinal, right? And then we said let me just quickly remind you this one before we begin with this. Today's lesson, by the way, the continuation of that, we're learning more properties of that, but starting with a transverse wave in here, we said the highest point on a transverse wave we call a crest, right? The lowest point on a transverse wave, it is called trough, right? And then if we extend this one here, we said maximum displacement from the equilibrium position, that is called amplitude, right? And then the distance between two adjacent similar points on a wave, we call that wavelength. And of course, you can take any two similar points, so it doesn't have to be from crest to this crest, or from trough to another trough, or from any other point. It could be to the same exact point on the next wave. That is going to be one full wavelength. Okay, but remember, this side here, it must be written displacement. Okay, so this would be maximum displacement either up or down. You can call that amplitude. And you can see that here, if we take a particle, this is a transverse wave. If you take the motion of a particle here, this particle, it can move either up or down, which is at a right angle to the direction of wave travel. But if we, for example, think of a longitudinal wave in here, something like this one, we said we call this region of a longitudinal, so we call this region compression, right? And we call this region, if it is a spring, we call it stretch. All right, so compression and compressed, and this will be stretch. Okay, and then we said the particle here, it can only move back and forth while the wave is traveling in this direction. So these two are parallel, while here it is perpendicular to the direction of wave travel. All right, so these are the things that we've learned so far. Now, today we're going to talk about some other properties of this wave. And so this is the wavelength. We've already talked about this. We said it is the distance between two adjacent similar points on a wave. Don't forget, but these 2 points both must have the same speed and direction so that we can call the distance between the two one wavelength. And normally wavelength, it is measured in what? You can say it is measured in meters here. Measured, right? Measured in meter. Don't forget this. Okay, now what about wave speed in here? We can say wave speed is, in general, it tells you how fast the speed is moving or traveling in that medium or in empty space. It doesn't matter what. So we can say it is the rate at which a wave travels through a medium. And since it is wave speed, so that is measured in meter per second. Now, another thing, or you can say two more things that we have, it is frequency and period. We've already learned about frequency and period before, right? So now, if we have a wave, we can say frequency, that would be the number of waves or oscillations per unit per unit time, or in a certain time. So this would be the frequency. And then period would be the time for one full oscillation, or the time that one full oscillation occur. That is also, we can call that period too. Okay, so frequency, that'll be the number, don't forget, the number of waves that passes a given point of a unit time. And also we can say that is frequency. Period will be the time required for one complete oscillation, right, of a vibration of one particle here. That'll be the period in here. So if we want to, for example, don't forget this, let me tell you a few more things regarding this one, like in terms of equations here. The first thing we were talking about was wavelength, right? And then after that, we're talking about speed, speed of a wave, and then frequency, and then period. What is the relation between each one of these in here? We've learned about wavelength, right? So now, what is speed? Now we know that speed, it is equal to, like previously we've learned that speed, it is equal to delta x over what? Over delta t in here. But if we're talking about, for example, the speed of one wave here, what would be, consider a transverse wave in there. The distance between, for example, or the distance that is traveled by a point or one full wave here, that is going to be wavelength, right? So how much or how far is it traveled? That is going to be delta x. Delta x represents the wavelength in here. Okay, so instead of delta x, we can just write the wavelength for the displacement or for the distance that is traveled by this wave. And then regarding the time, if it is the time for one full oscillation, don't forget, isn't that one period or just the period? Yes. But now I can rewrite this one here. We can say wavelength times 1 over the period. Isn't that the same thing as what we just wrote? Yes. Now instead of 1 over period, we'll just write what? We'll just write frequency. So now this would be a new equation, and you can call this one wave equation here, or the speed equation for a wave in there. Now regarding this two, you already know that. We said whenever we have frequency or frequencies mentioned, you can always use this two equation. If the number of wave is given, we'll say number of waves, oscillations, cycles, or whatever divided by the time it takes. If not, if you have the period, you can say frequency is equal to 1 over the period, and that would be the frequency. And we also have this equation too. We can say frequency 1 over the period, and these two are inversely proportional. So we can say period, it is equal to 1 over the frequency. And if you multiply the two together, of course, you'll get what? You'll get 1. Of course, sometimes you'll need this one. If the frequency or the period changes by a factor, then it is totally fine to use this equation as well. All right. Now, going back to this one here, one more time. But don't forget, this is we can say diagram for a transverse wave. Don't forget the details. We have crest, trough, amplitude, and the distance from one point on a wave to the same adjacent point. That is going to be one full wavelength. I would say or here, it doesn't matter. And that line here is going to be the rest position here. This is the displacement measure. And this distance here, you can say how far the wave travels, all right? So don't be surprised if you see, for example, x in here, okay? Or some other times you might see delta t here, like as a function of time, like how long does it take when the wave is getting here. So, but for now, you can just think of it as x, for example. Don't forget, by the way, there is one more thing here. If we're considering that'll be, or you can say x would be the equilibrium position for the particles there. Now, we've already talked about these, but let's just go back and emphasize on this one too. The distance between two consecutive crest or trough, these are equal to what? The distance between two consecutive crest, that is one wavelength, or trough, that is one wavelength. But the distance from a crest to the adjacent trough, that would be the distance from this point to this point, that is equal to what? If this is one full wavelength, isn't that half a wavelength? Yes. So this is half and this is half. Okay? So don't forget that is going to be half a wavelength. And the distance between, watch this one, the distance between three consecutive crest or trough, that is equal to 2 wavelengths. What do you mean by this? Now let's add one more in here. So for example, now I have 3 crests now. So that is 1, 2, and 3. Okay, so remember the distance between these two, that is 1 wavelength, and this two is going to be 1 wavelength. So the distance between 3 crests, it is equal to 2 wavelengths right here. All right. Now, moving forward, says frequency, it is the number of waves per unit time, which is measured in hertz, which these are, you've already learned all of these before. So now if you ever want to calculate frequency, you can say frequency 1 over period, or the number of waves per unit time, which is, if the number of waves is given, this is the equation that you need to use. What about period? Once again, it is the time for one complete oscillation, and that, because it is a period, it is measured in second. Frequency measured in hertz, and then period, it is measured in second. And this is how we can get the wave speed equation. It minus delta x over delta t, but the distance that is traveled, that is one wavelength. So the speed, it is equal to delta x over delta t. Well, delta x is the distance traveled by a wave. If it is by one wave, that would be the wavelength. The time would be, the time for one full oscillation is going to be period. So now we can say 1 over period times the wavelength, which is frequency times wavelength. Of course, we get into this equation right here. Now, there are a few things regarding, or a few study tips regarding this this equation I need to tell you here. And these are very important because you will need it for solving, or sometimes for multiple choice questions. Sorry. So we can say speed, it is equal to frequency times wavelength. Now you need to know that these things, for example, okay? Now the speed of a wave, when a wave is passing through a given medium, the speed of a wave is always constant, Basha. The speed of a wave in a given medium, it is constant, unless the physical property of the medium change. But, for example, we have two waves, Basha. One of them has a frequency of 120 hertz, and then there is another wave that has a frequency of, let's say, twice as this, let's say 240 hertz, Basha. This is 120 and this is 240. Can I say because the frequency of this one is twice this much, the speed is twice? No. Remember, as long as it is in the same medium, the speed will always stays the same. So now, in order to help you understand this one better, let me just draw something very simple. The speed of a wave, right, it can only change by two things here. By changing the medium, so you can just write m for the medium. Let's say medium here. It can change by changing the medium, or the speed can change by changing the temperature. Okay? That is the only two things that can change the speed of a wave in a given medium. All right? And then what about the frequency? The frequency is a little bit different, actually. If we don't change the medium or the temperature, it will never change. Okay? So we can say the frequency can change only, all right, by changing what? We can say by changing the source, all right? Source. What do I mean by changing the source? For example, now when I talk, I have a certain frequency. When you talk, you have a certain frequency. So our voice is different. That is because our frequencies are different, right? So we have different frequencies there. So frequency can change by changing the source and also by changing the temperature only. If the temperature doesn't change, frequency will never change. And that is only true, by the way, don't forget, that is only true for mechanical wave. For mechanical. For electromagnetic waves, even if the temperature change, the frequency will never change. So make sure you know this one here. What about the wavelength? Now, of course, wavelength, and we can see that if the speed changes, the wavelength will change. We can see that. So when will the speed change? Of course, by changing the medium, or if by changing, we can say by changing the medium, all right, or by changing the speed in here. So if the speed change, the wavelength can change. We can say by changing the source, all right, the source, and of course we can say the medium too, all right, because we said that our speed in the same medium is the same, but if we have different frequencies, that means our wavelength is going to be different as well. So remember this, make sure you know this one now. So I'll give you some examples now. The speed can change by changing the medium or by changing the temperature. Frequency can change only by changing the source, the thing that produces the frequency, like a different source, a different object, or by changing the temperature of a medium. While the wavelength can be changed by changing the source or by changing the medium. Basha? So now we have a question here, says what? Says if a wave go from if a sound or a wave goes from one medium to another, from one medium to another. Basha, we have a wave, okay? This wave, it is going from one medium, let's say medium 1, all right, medium 1 to another medium here, Basha. So once it goes to another medium, what are the things that can change, or what are the things that will not change once a wave go from one medium to another here? So now the first thing you have to analyze, for example, the speed of a wave. Can the speed of a wave change? Yes, because we said that if the medium change, the speed will change. So you can see that there is medium change, so the speed of a wave will change. That is the first thing. Now regarding the frequency, now frequency can only change by changing the source or the temperature. Are we changing the source of the temperature here? The answer is no, because if temperature is not mentioned here, that means temperature stays the same. So the frequency will not change, Agad Basha. So frequency doesn't change. What about the wavelength here? So we said the wavelength can change by either changing the source or the medium. Now, because the medium is changed, so the wavelength will change as well. So what is the only thing that it doesn't change? It is the frequency. So you can use this, of course, to answer any question that is related to the wave when something changed there. Okay, so that would be the answer to this question here. Now, going back to the study tips, which is all about this one here, you can say, and that is the first thing we have, says the speed of a mechanical wave is constant for any given medium. If the medium doesn't change, the speed of a wave will always remain the same, unless if it mentions the temperature change, that would be the next point here. But if it is in the same medium, Basha, the speed will always stay the same. But as many times in Wizari, they'll tell you we have 2 waves or 3 waves, one of them with this much frequency, the other one with this much and that much. They have different frequencies. They might ask you which one of these travel the fastest. Be careful, Baba, because it is the same medium, the speed of the wave will not change even if they have different frequencies. Yeah, that is the first thing. The second thing is, says the speed of a wave change when the wave moves from one medium to another. So if you remember the map, we said the speed can change if a wave goes from one medium to another, because the density of the medium change, like how close or far the particles are from one another, will change. That affects the speed of a wave. So of course, in that case, the speed of the wave will change in here. So, and that is one of the reasons where the speed change. But what if the temperature of the medium change too? That also affects the speed of the sound bubble and the speed of a wave in a medium. Later on, you will see that, for example, once we increase the temperature, that increase in temperature makes the wave travel. If it is sound waves we're talking about, it makes it travel faster through air. So changing the temperature will change the speed of the wave. The next thing that we know that frequency and wavelength are inversely proportional to each other, so be very careful with that. For a given medium, if we said the properties doesn't change, there is a certain speed. If you increase or decrease the frequency, of course the wavelength will change inversely, because the relation between the two is inversely proportional. Okay, now what do you mean by inversely proportional? Going back to this equation here, right? If I just want to add a little bit more to this here, now speed dakata, frequency times wavelength. Well, now what if I want to find the frequency? That is equal to what? That is equal to speed over the wavelength. And if I want the wavelength, that is equal to speed over what? Speed over frequency. So what is the relation between each one of these, Baba? These are inversely proportional. You've learned that if 2 things are above the fraction, these are direct. If one of them is below, that is inverse one, yeah? If the speed is constant, if the wavelength increases, frequency decreases, and vice versa, we can say. And if the frequency increases, the wavelength must decrease. So these are inversely proportional, and you need to know this one. All right, the next thing that we have says what? Increasing, now that's still related to that. Increasing the frequency, decrease the wavelength, and vice versa. We can say that in a given medium. Number 4 says the frequency can change by changing what? By changing the source or by changing the temperature. We said there are 2 factors that affect the frequency, and these are, we can say frequency change by changing the source or by changing the temperature of a given medium, we can say, or the temperature of a medium here. Okay, but remember, these are only for mechanical waves. This temperature change cannot affect the electromagnetic waves in here. Okay, now the next thing, the fifth one says the wavelength can change by changing the medium or the source. That is also something you need to know. But electromagnetic waves are unaffected by the medium temperature, so the frequency will always remain the same or fixed. All right, so we have a question here. It says, if a wave travels from one medium to another, this is the question we were just solving, Basha, says of a higher density, so the properties of the medium will change, it says which of the following remains the same here. Basha, because the temperature is not mentioned, Gutman, speed, the frequency times the wavelength here. Gutman, this one can change by changing the medium or the temperature. This one can be changed by changing the source or the temperature, and this is by either we can say the source or the medium. So now only the medium is changed, so the speed will change, the wavelength will change, but the frequency will remain the same, and that is where the answer is, the frequency. The next thing that we have says sound waves from different instruments reach our ears at the same time, even though they have different frequencies. Why is that? For example, let's say there are different musical instruments, a guitar, a piano, I don't know, a clarinet or whatever, like once these are played, or when people are talking, for example, simultaneously, we can hear them all at once, even though they have different frequencies. So why do we hear them at the same time? That is because the speed of a wave, it is the same in a given medium. Masha, I got it. That'll be the answer to that question. Okay, the next thing we have says, what does the speed of a wave depend on? That is also a very interesting question here. Of course, speed of a wave depend on three factors. The first thing we can say is the type of the wave in here. Now, what do you mean by the type of the wave? Ebasha, we have sound waves that are, you can say, fast enough, all right? And then if you think about water waves, okay? Now, if I ask you to compare which one is faster, sound waves or water waves? When I say water waves, like could be water waves in the ocean or surface on a pond. Of course, sound waves are faster one, yeah? Now compare the sound waves to the electromagnetic waves, like light waves. Now, which one is faster? Of course, the light waves are faster. So now, the major thing that it determines or affects for example, the speed of a wave would be the type of a wave, Basha. The type of a wave determines how fast the wave is traveling. That is the first thing. The second thing that we have is the properties of a medium. Of course, we know that waves can travel in different mediums, right? Now, if we talk about sound waves, be careful, Baba, because there's a difference between, be careful with, or just listen carefully to what I'm saying. If we have a sound waves, right? This sound wave can travel through air, can travel through water, and can travel through solid too. If I ask you in which one of these sound waves travel faster, of course, if it is your first time hearing this, you're going to say immediately, you might say sound is traveling faster in air. That is because you've learned that light travels the fastest in air, which is almost very likely it's the same as the speed of light in a vacuum. So remember this, Baba. If I ask you, we have three different mediums, air, solid, and gas, Basha. So liquid, solid, and gas. In which one of these a sound traveled the fastest? That would be solid. I got Basha. We're going to study this in chapter 4, but just, giving you an intro or a heads up, you could say. So sound travel the fastest in solid. Why? Because the particles in the solid are closest together. Right, now put that aside. But if the question is about light waves, which you've learned before in grade 11 or 10, let's say, in grade 10, light, like the denser the material, the slower the light. So light traveled the fastest in vacuum, in air, which is pretty much almost like same as in vacuum, Basha, that it traveled slower in liquid, it traveled the slowest in solids. That is for light, Basha, electromagnetic waves, you can say. But it is exactly opposite for sound. It travels the fastest in solid, then it is slower in liquid, and then the slowest in gas, because the particles in gas are the furthest apart compared to the other. And then the last thing that it depends on is if we're talking about sound wave, it depends on the temperature. We can say the higher the temperature, the faster the speed of sound will be. But Agalibi, this temperature, you can add one more thing. You can say this is only for mechanical waves. Only for what? For mechanical conical waves, or right, you can say more specifically for sound. Basha. Otherwise, for electromagnetic waves, these waves are unaffected by the temperature. Okay, question 21. These are the kind of question you need to be aware of them, and of course, the easiest way to solve them is like this. It says, what happens to the wavelength of a wave, right, on a string when the frequency is doubled, right? And then the next part, it says, what happens when the speed of the wave, what happens to the speed of a wave as well. So you can write this equation, frequency times the wavelength. It is easiest to do this one here. It says, when what? When the frequency is doubled. If the frequency is doubled, we've learned that whenever it says doubled or whatever, make that into a fraction, and then just use the reciprocal of this fraction. If the frequency is doubled, the wavelength, it is going to be what? 1 over 2. Why? Because the speed, it is constant here. Because the speed is constant. If the speed is constant, if this one increases 2 times, this one must decrease 2 times. And of course, you can use this equation too. Frequency and wavelength are inversely proportional. So if that is the case, you can see that it is 1 over, for example, that would be this. If the frequency is doubled, if the frequency is doubled, so you could just write 2 in here, so the wavelength that is going to decrease by, or becomes half. So here's the frequency. If it is doubled, this is what it becomes. So the wavelength becomes half, and that is the answer. So whichever you use, I believe it's best to use this one here, because as long as the speed is constant, yani whatever the factor you're using, you should get the same answer. Then it is correct. Okay, the next thing, by the way, I forgot to mention it here. What happens to the speed, by the way? The speed of a wave will not change. Because if this is double, right, this one becomes half. So now this two will cancel out. So the speed will always remain the same here as long as no property of the medium change. All right, the next question that we have says what? 2 tuning forks. These questions are, if you're not careful, of course, you might make a mistake at this one. So careful here. It says we have 2 tuning forks with frequencies of 256 and 512. All right. So you see the frequency of this one, it is twice. If this is one frequency, this is 2 times that. Rasha, this is 256, this is 512. All right. So these are the 2 frequencies of tuning forks when they are struck. The question says, which of the sound will move faster? Now, just because it says faster, it doesn't have to be faster, by the way. So once again, you might just say because this one has a higher frequency, so this one travels faster. But we've said that, Baba. As long as it is in the same medium, which is mentioned here, in air, and no property of the medium change. So as long as it doesn't mention anything of change, so it is everything else is the same. So in this case, of course, the speed of sound or the speed of the wave will be the same. So the speed will always remain the same. So we can say the wave or the wave they have the same they have the same speed because the speed of sound in air remains constant. Now we have a few questions here. These are also very important to answer them. The first one says, if the frequency of a pendulum is 1 hertz, Basha, if the frequency is 1 hertz, Basha, what is the period of this pendulum here? Okay, let's solve this one together. These are easy questions. I expect you to be able to do them very easily, and you could give it a try before I start. Basha. Okay, it says if the frequency is 1 hertz, what is the period? Because because there is frequency given, we have this equation, frequency dakata 1 over period. So we want the period. 1 over frequency dakata 1 over 1. So it is going to be 1 second, and that'll be it. So which one is this? That is going to be option A. All right, the next thing that we have, what does it say? It says the number of, watch this, the number of cycle of vibrations per unit time. Because it says number of vibrations per unit time, isn't that frequency? Yes, so that is frequency, as easy as this, which is option C. Another question that we have says, what happens to the wavelength of a wave when the frequency is doubled? We just mentioned that, if the frequency is doubled, then the wavelength becomes what? Becomes half. It's because speed dakata, frequency times the wavelength. If the frequency is doubled, that is 2 over 1, so this becomes half. So which one is half? Increases twice, increases to triple, means 3 times. decreases to half, that would be the correct answer right here. Okay, so we can say the answer to this question, it is C. All right, now the next one is question 4 says what? It says a harmonic wave is traveling along a rope. The oscillator that generates the wave completes 40 vibrations in 30 seconds. Find the period of the source. Now remember, because we're given the number of vibrations, so always use frequency equation here. We've learned that frequency, dakata, right? What is frequency equal to here? Right, frequency it is equal to, because the number of vibrations given, Basha, number of vibrations per unit time here. So how many vibrations are there? 40 vibrations in 30 seconds, right? So once you divide the two, that is going to be 1.333. And if you're not careful, you're just going to choose that, and this is how you're going to lose 2 marks very easily, Kaka. Remember, the frequency it is equal to 1.33 hertz, Basha, but we want the period, not the frequency, and we know that the period is equal to 1 over the frequency, right, which is going to be 1 over 1.333, and then what would that equal to? I think it is, which one is it? It is 0.71, yeah? So 1 divided by 1.33, so it is going to be 0.7, and that'll be the correct answer here for this one. All right, now another question that we have is this one here. So there are a lot of questions actually. We'll try to see as many as we can, but of course without losing much of a time. It says 3 sound sources. The frequency of the first one is this much, the frequency of the second is this much, and the third one is this much. It says which of the sound will move faster through the air. As long as it is the same medium, then we say, but do not fall for these tricks. They give you different sounds with different frequencies, but as long as the medium is the same and then no other properties have changed, the speed of the sound will always be the same. Yani, none of them will be faster than the other one. So the question says which wave or which sound will move faster. So we can say all of them have the same speed one, yeah? This one says the first one, this is the second or the third one. No, all of them have the same speed. Question number 6 says, what happened to the wave speed in a vibrating rope when the frequency is double? That is the same as before. 7 says, what happens to the wavelength in a wave on a string when the frequency is doubled, and what happens to the speed? We also said that one, yeah? Good man, if the frequency is doubled, the wavelength becomes half, but the speed remains the same. This is another question which I would like to solve. This one for you here says what? This is a nice question here. It says 2 tuning forks are struck, Basha. The first one produces a sound with a frequency of this much, 285, with a wavelength of 1.5, Basha. And the second tuning fork produces a frequency of this much, Basha, of this much. What is the wavelength of the sound produced by the second tuning fork? Now for this question, there are 2 methods you could do that. I'll show you both methods inshallah. So the first one here, we have, what do we have? We have frequency and wavelength, right? So speed, dakata, frequency times wavelength. That is for the first one. F1, wavelength 1, we can say that. So that is going to be 285, all right, times 1.2. So using this 2, we can find the speed of a wave, 285 times 1.2. So the speed of a wave in a, or the sound in air, or in that medium, it is going to be 342 meters per second. Now, isn't that the same medium? Yes. So as long as it is the same medium, we can use the same speed for the second wave. So we can say for the second wave, that is F2 times wavelength 2 here. The speed is the same medium, so it is still 342. Okay, 342, it is equal to, the second frequency is 570. Now you can find the wavelength here. So how do you find the wavelength? You just divide the two, 342, divide by 570. Let's see, what is this equal to? That is 342 divided by 570. The answer is going to be 0.6 meter. That is the wavelength of the second wave here. But what is the second, what is the other method that we can use for this one here? Now you can use cross multiplication method. What do you mean by cross multiplication? Now we know that we can say, watch this, V dakata, F1 times lambda 1, yeah? And of course V for the second one, it is F2 times lambda 2. Or you can write them side by side. I think that'll be better here. So the other one here, speed دكاتة, frequency f2 times wavelength 2. Masha? Now you could say this instead, when you believe these two are equal, when you but just remove this one here because they have the same speed. Kata, this side and this side must be equal. Now you can make an equation out of this. We can say, Basha, because frequency and wavelength are inversely proportional, so don't forget, we can say wavelength 2, because this is what we're looking for, over wavelength 1, Basha. You could just cross multiply in there. That is going to be f1 over f2 there. This is how easily you could do that here, Basha. So you can use this equation at any point as long as the medium is the same. So now wavelength 2, it is unknown. Wavelength 1, it is 1.2. Basha, f1 with the first frequency, it is 285. And then the second one, it is 570. Basha, find this and you can multiply by 1.2. That would be wavelength 2 here. So let's do that again. 285 divided by 570. All right, the answer is going to be half, Basha, or 0.5. 0.5 times 2, times 1.2, the answer is going to be 0.6, which is the same thing. So once again, wavelength dakata, Gutman, this is 0.5. Okay, that is 0.5 times this 1.2. The answer is equal to 0.6 meter, which is exactly the same as what we have just found before. Yeah. So whether you use this method or this one, it doesn't matter as long as you're using this correctly. All right, because these are inverse. I got this 2 and 2 together, and 1 together. This is when two things are inverse. This is how you're supposed to write them so that you could do the calculations correctly. All right, the next thing that we have says, which of the following sound wave travel faster in air? You have to be careful here, right? So once again, as long as, like it's the same medium, the speed of sound will always stay the same, right? So don't fall for these tricks. Audible waves, all right? Infrasonic waves, ultrasonic waves. Aren't these are all audible sound waves? Yes, right? And then, of course, by the way, this would be best, I mean, if it was with chapter 4, but as long as it is the same medium, we could do this one too. As long as these are in the same medium, kata, they have the same speed. By the way, what are these type of sound? We'll explain in chapter 4. Audible, these are sound that we can hear them. Infrasonic, we don't hear them. Ultrasonic waves also, these are sounds that we don't hear them either. But these are all kind of sound waves here. So it is going to be all of them have the same speed. Basha? Now, we have a few questions to begin with, right, or to solve this one here. Remember using the equations we've learned. The first one says, a string vibrates with a frequency of this much. So there's a frequency. We have frequency gets under 264 hertz, Basha. Assuming that the speed of sound in air is this much, the question says what? That's meter per second. Find the wavelength of the sound wave produced by the string here. We've learned that speed, it is equal to frequency times the wavelength, right? And then we want the wavelength here, so we could just plug in the numbers or find this one. Yeah, well, let's do this one here. So the speed, it is 343. It is equal to frequency 264, and then find the wavelength here. So just move this number, divide both sides by 264. You'll find the wavelength. And the wavelength, it is equal to, I think it is 1.3 meter here. Basha, this is how you can find the wavelength. All right. The next question that we have says the speed of all electromagnetic waves in empty space is this much. Okay, the speed of electromagnetic wave, it is 3 times 10 to the power 8 meter per second. Calculate the wavelength of the electromagnetic waves emitted at the following frequencies here. So the first one says radio waves, like at 88. Remember, this is megahertz. Now this mega, you have to convert this one to hertz, so you have to convert to the mega here. So how do we do that? Once again, the question says find or calculate the wavelength, right? So yalla, do that. Wave speed dakata, frequency times the wavelength. If you want the wavelength, dakata, speed over che, the frequency. Yalla, speed dakatsanna, 3 times 10 to the power 8 meter per second divided by these frequencies. The first one, it is 88 mega. Remember this, mega, you've learned that in grade 10, that is equal to 10 to the power 6, that is million, right? So you need to know this one here. Okay, so that is 88, all right, times 10 to the power 6, which is mega or million here. So you just divide this two, you'll find the answer. Okay, yalla, what is the answer to this question now? The answer, it is equal to 3.41 meter. 3.141 meter, and this is how you can find the wavelength. This is for the first one. You'll do the same thing for part B and C, right? But don't forget, again, you'll have to, or you need to convert the mega, and then you can easily get the answer right. Okay, we have another question here. It says a tuning fork produces a sound with a frequency of this much, and a wavelength in air is this much. What value does this give to the speed of a sound in air? All right, so this is pretty easy as well. We could just say that regarding the speed, it is equal to frequency times the wavelength. You have the frequency, which is 256, wavelength, that is 1.35. Just do the math, of course, you'll find the speed, which is 346 meter per second. That'll be the first part of the question. Now, the second part is also important here. Now, watch this. All right, if you're not careful, of course, you might kind of like pause for a minute until you get what exactly is this. So the second part of the question says, what would be the wavelength, all right, the wavelength of the same sound in water, right, in which the sound travels at 1,500 meter per second. So what is the keyword here? Like, why do they say of this sound in here? Because remember, for the second part, the only thing that they'll give you here is the speed of sound. Basha, if we want to find the wavelength, the speed over the frequency, the speed is 1,500. So the reason why they say this or the same sound here, because even if that sound go from one medium to another, will the frequency of the sound change? No, right? In this case, so when they say of this or same sound, that means use the same frequency, or the frequency doesn't change, that is 256. So you do the math, that is going to be what? 5.8 meters there. All right, so remember, the key here is to know that when a sound goes from one medium to another, the frequency remains the same because only the medium has changed, nothing else. Okay, another question here, and that'll be this one here. This is one of the questions that we have actually that is very, very important. And this question been in Wizari multiple times. All the ideas circulate around these kind of, let's say, questions. So I need you to be really careful once you solve these kind of questions. All right, so let's solve this question together. Right here, what does this say? We have a wave, as you can see. Masha. All right. So as you can tell, let's zoom out this one a bit. All right. All right, let's say this one too. Basha, this is what we have. So what does the question say? The question says, a wave traveling in a positive x direction with a frequency of this much. So don't forget, you have frequency, and the frequency is 25 hertz. It is shown in the figure below. Find the following values for this wave in here. The first thing you need to find is the amplitude in here. But what is the amplitude here? If you remember, we said amplitude, it is the maximum displacement, either up or down. But what is given here? It is the total, you can say, that is the distance from the top of the wave to the bottom is given. So if it is 18, how much is just a distance from the equilibrium to maximum displacement up? Isn't that half of 18? Yes. So regarding the amplitude for part A, we can say it is equal to, you can say 18 divided by 2, because that'll be both up and down. So you just divide by 2, it is equal to 9 centimeter. Also at this point, you can look at the choices. If the givens with the choices are in centimeter, you can keep it. If not, you can convert this to meter. That is going to be 0.09 meter here. That is the answer of the first question. The second part says, find the wavelength. Now I need you to be careful here as well. All right, so how do you find the wavelength here? Remember, this thing here, or if I start from this point here all the way, the distance from this point here all the way to the next crest, that is going to be what? That is going to be one full wavelength. But how much of a wave is shown here? Didn't we say earlier that the distance from a crest to a trough, it is half of a wavelength? Basha, if not, you could, for example, use this one. Isn't that half of a wavelength? Yeah, so part B, we can see that half of a wavelength, it is equal to 10 centimeter. Basha, what about one full wavelength? You just cross multiply one full wavelength, dakata, 2 times 10, which is equal to 20 centimeter. That is if you, for example, 1 centimeter, but if you want to convert to meter, the wavelength is equal to 0.2 meter. Basha, what the Krila Persari, for example, instead of giving you all that, they might give you, for example, a section of this. Let's erase this one. What if they were, instead of drawing all this, they just did something like this? What if they said the distance up to this point is, only this point, for example, is 10. Now, how much of a wave is this? Now, the easiest way to do this is, watch this, Baba. Draw one full wavelength, all right? So if only this distance is given, you can divide this into sections. That is 1/4 of a wave, yeah? That is 1/4 of a wave, right? Some other times, some other teachers, let's say, prefer to go by amplitude here. This would be, for example, 1 amplitude. This is going to be 2 amplitude. This is going to be 3 amplitude in here. And this is going to be the 4th amplitude. So previously we said there are 4 amplitudes in every wave, but once you're doing this, you really have to be careful because we don't want you to make any mistakes. So I most of the time avoid this because you might sometimes just consider this as 1 amplitude and that'll be incorrect, okay? Because if this is a particle here, if this is a particle, it has 1 amplitude, let's say, to go up, and there is another one to go down. So there are 2 amplitudes right here. That'll be 1 and 1 for, because that is going to be half a cycle, yes? So 1 for going, 1 for coming back. So that'll be 2, and this is going to be 2. That is a total of 4 amplitude, which is 1 full wavelength here. But whichever the method that you're using, as long as, for example, you know how to use it, that is perfectly fine. And of course, you can keep using that method. But if not, you can always remember this. That is from a crest, we can say, or trough, that is going to be 1/4 of a wave, or something even better. We said the distance from a crest to a trough, it is half a wavelength. If this is half and this is right the center of that one, yeah? If the center of that splits it to 2, so this is 1/4 and this is another quarter, and then this quarter here. If 1/4 is 10, we can say that 1/4 of a wave, dakata 10 kata, what is 1 full wavelength? That is going to be 4 times 10, which is going to be 40 centimeter. Also, you can convert that into meter. When do we use this? If only a quarter is given, which is pretty much possible in Wasari. All right, so that'll be the wavelength, but in meter, don't forget. All right, now the next thing that we have, part C says find the period. Okay, now I need you to tell me how you can find period on this diagram here. Now keep looking around here. So what method can you use to find the period on the diagram? But be very careful, Baba. Now I know all you focus on the diagram, and this is how you make mistakes in Wasari. Baba, look, once, for example, you want something and you can find it on a diagram, go back to the question and read that. Okay? Now, if you go back to the question, because the key is inside the question, not on the diagram here. So at any point, Baba, if, once again, if a diagram is given and you're looking for something, you don't get it, or you can't find it, or you don't see that, always go back to the question, read it over and over, because if you can't find it here, there must be a key hidden inside the question so that you can use to find the answer. Frequency. So this thing says find the period here. There's no way you can find the period here based on what is given here. But because frequency is given in the question, so period dakata 1 over frequency, right? That would be C. So again, period dakata 1 over 25. So what is the frequency now? Just do the math. You'll find the frequency, which is equal to 0.04. 0.04 seconds. That is the period based on the frequency that is given. The last thing that we have, the question says, find the speed of the wave. We found the wavelength one, yeah? And the frequency is given. Can I find the speed? The answer is yes. So speed equal to frequency times what? Times the wavelength. Okay, but remember now the wavelength must be in meter, don't forget. So the frequency is 25. The wavelength it is or was 0.2, my bad, almost forgot. 0.2, Basha. Now do the math, of course, you'll find the answer. 0.5, 25 times 0.2, what is that equal to? That is equal to 5 meter per second. 5 meter per second, that'll be the speed of this wave right there. See how easy the questions are if, of course, you're careful and cautious here so that you can find your keywords here. The next question that we have, question 26, says what? Microwaves travel at a speed of this much. When the frequency of the microwave is this much, what is their wavelength? I believe you already know how to answer this question, so you can give it a try. All right, now question 35 is also something very important, and it's been in WizIDU recently as well. So let's solve this one together. And I need you to focus here as well. All right, what does it say? It says, Lawan dips his finger into a pan of water twice each second. So here's, we have, let's say, a pan of water, and this is the surface of water, Basha, as you can see here. So imagine instead of, like he's basically dipping his finger into the pan of water, but here's what we're going to do something else. Instead of dipping, like for example, the finger into the water here, I'll just tap on my, for example, on my hand here. Isn't that the same thing? Imagine, let's say my hand is the surface of the water. Every time you tap on a water, there will be a ripple or a wave spreading, right? So that is a wave here. So we can say every time you tap, that is producing a wave on the surface of water. So the question says, he's doing that, right? It says twice each second. What does it mean? That means he's going to tap 2 times in 1 second. So 1, 2 in 1 second, 1, 2 in 1 second. So Basha, what can we use this information for? Isn't that the number of waves per unit time? Yes, but what does that help you to find? The frequency. So remember, we can use this information given to find the frequency, because we know that frequency, the number of waves, Basha, or you can say cycles, oscillations, vibrations. Here you can say number of taps, right? These are all the same thing, by the way, Basha. Divided by what? Divided by the time. So how many times is he doing that? Is doing that twice, tapping or dipping, doesn't matter here. All right, so twice each second, that means the number of waves is going to be 2 every second. So the frequency, it is going to be 2 hertz. And that is the first part of the question. The next one says, producing waves with crests that are separated by 0.15 meter. So remember, this is the surface of a panel, whatever. So once you're doing that, of course, it produces waves that are spreading like this. But if you look at it from the side, this is how it looks like in here. So these crests are what? How far are they from one another? It is 0.15. But isn't this the distance from one crest to another? Isn't that one full wavelength? Yeah, so now the wavelength, we can say it is 0.15 Basha meter. This is how far from one another. So this will be the wavelength. All right, so we have the wavelength and now we have the frequency. The question says determine the frequency, period, and speed of these water waves as well. We've already found the frequency now, Wanya. So you can call this is the first requirement. Now let's just write this one a bit smaller now. So we said 2/1. So the frequency is 2 hertz. That is the first requirement. The second requirement says find the period. If we find the frequency, we can find the period too. So period 1/frequency, 1/2, that is 0.5 seconds here. Basha, 0.5 seconds. Or let's just write S for second here. That is the period. The next thing says find the speed of these waves. All right, third requirement, speed the frequency times the wavelength. Basha, frequency كمان سنبو 2. The wavelength that is 0.15 here, which is going to be 0.3 meter per second. That is going to be the speed of these water waves there. All right. Now the next thing that we have, it is also easy, says, what does it say? It says the notes produced by a vibrating string range in frequency from approximately 196 to this much hertz. Find the possible range of the wavelength in the air produced by the string when the speed of sound is this much. Whenever the question tells you find the range, of course, you will have to find two numbers starting from the minimum to maximum. This is how you can find a range in here. So what do we have? Here now we have two frequencies, right? Or the frequency range that we have, it starts from 196 to 2670 or 37 hertz in here. Okay, since the speed of sound is the same, right? So what is the speed of sound? It's 340. And then here it is also, we can call this one 340 here as well. Let's write these. Now watch this, Baba. Here's the first frequency and this is the speed. What can I use this for? If I use this to information, can I find the wavelength here? Yes. Okay, that is one wavelength. What about this two? If this is, we can call this one F2, since it's the same speed, that is V. So I can also use this two to find another wavelength. So you can call this one wavelength 1 and wavelength 2 here. Yalla Bashir. But remember this, we have two things you need to know. Frequency and wavelength are inversely proportional. If the frequency is the least, the wavelength is going to be what? The largest here, Basha, or the longest here. Here, frequency is the highest, Basha, so the wavelength that we should get here, it should be the smallest or the shortest in here. Yalla Baba. So wavelength the speed over the frequency. Yalla, speed kaman sanda 340 divided by 196. So of course we get a number. What about for this one here? That is also speed over frequency. You can say V over F1, and this is V over F2, which is equal to 340 divided by 2637. So you just do the math, you'll find the wavelength. Let's take a look at the ranges here. What are these numbers? One of them is 1.73. 1.73. It is 0.129. This one is 0.129. Ebash, if you want to find or write this range, right, how do you do that? Normally you write from the smallest to the largest. So this wavelength now, or the smallest wavelength, it is 129, 0.129, and the largest it is 1.73. Kata, as a range here, we can say that, okay, the wavelength that we have, it is larger or equal to than this, but it is smaller or equal to this much here. That is as a range. Agarishna, you could just write starting from 129 to 1.73. That would also be fine because that would be the range for the wavelength that we have. All right. Now, waves transfer energy. This is also something very important. And what exactly does it mean? If you remember when we were talking about waves first, the previous lesson, we said when you throw a pebble into water, of course, this pebble creates a disturbance in the water, Basha, and then these disturbances produce ripples or waves will spread across the surface of water, okay, moving away from the center of the disturbance. But we also said that if you notice, the water, it is only the waves that are traveling. The particles or the water molecules, they only vibrate, let's say, or move up and down, which is at right angle to the direction of wave travel. To simplify this even more, the water molecules are not being displaced. They do not go from one place to another. They don't go along the wave, okay? It is only the wave that is going. But we know that waves transfer energy, right? So only, or we can say only the waves only transfer the energy, but not the particles of the medium here. But now, what is the relation between waves and, for example, or to be more specific, let's say the amplitude of the waves and the energy here? Now, think of, we said if you throw a pebble, a small rock, what happens if you throw a larger ripple? Of course, that creates a larger water waves here. So going back to this one here, let's say you're throwing a small pebble into a pond of water. All right, so this creates a ripples, but this is, if you look aside, this is how it looks like. What if you're throwing, for example, a larger or a rock into water now? So now, of course, the ripples are going to be larger here. So if you look at the waves here, this is how it looks like. So you can compare this one. And by the way, just imagine, for example, the water the water waves when it's windy, for example. The stronger the wind, we can say the larger the water waves or the ocean waves. Now something even bigger than that. What about, or how about the waves of a tsunami? Have you ever, for example, seen that, how high they are? This is, like, because they carry, or they have a lot of energy, so they have a large of destructive force. So we can say when it comes to waves, Baba, there is a relation between the energy of a wave that carries with the amplitude as well. But the relation is, we can say, the energy of a wave carries, it is directly proportional to the amplitude of the wave squared. In other words, in here, so if I have two waves, here's one wave, Basha, and there is another wave in here. So now, which one of these waves are carrying more energy here? Is it the first or the second? It is obvious that is the second wave, because we've seen that the bigger, consider this as a water wave, the bigger the water wave, the more destructive they are. Okay, so what is the relation between the two? It is this relation, and you need to know this one. This is something very important. Now, of course, we also have something as a practice for you too, but before that, let's answer this question, right? So it says, what does the rate of energy transfer of a wave depends on? We'll say the rate of the energy transfer depends on the amplitude of the wave, which is directly proportional to the amplitude squared. Don't forget. Okay, so the greater the amplitude, the more the energy wave carries in a given time interval. So the next question, how does the energy transfer in a mechanical wave change with amplitude? We'll say energy transfer change with what? It is proportional to the square of the amplitude. So here's the equation. I need you to listen to this carefully. When it says, let's just go this one here. Okay, now when it says, this is the equation, amplitude squared, Basha. So now at some point, this been a Nuzari by the way, at some points, what if they say the amplitude of the wave, if the amplitude of the wave double, by what factor will the energy change? Baba, whichever the side is given, plug in the numbers into that side, you can find the other side. Because most of the questions that we have says if the amplitude changed by this much or this, what will happen to the energy? And there are other questions says if the energy becomes this much, by what factor should the amplitude change? You can find the other side. Basha? So at this point here, if the amplitude doubles, Basha, by what factor will the energy change? And you do know that amplitude is squared, so 2 squared, we can say that energy increases by a factor of what? By a factor of 4 times in this case, Basha. By 4 times. That is one of the thing here. Now the next thing, what happens if the amplitude becomes half of before? So the first one, if the amplitude doubles, we said, here's an amplitude. If it doubles, the energy increases 4 times. That is first. What if the amplitude becomes half? If the amplitude becomes half, Basha, what do you think will happen to the energy? We'll write the equation again. It is directly proportional with the amplitude squared. So now, once again, it is, we can say half, or in this case, of course, it becomes 1 over 2 squared. Basha, 1 over 2 squared becomes what, Baba? Becomes 1 over 4, because this 2 squared. So in this case, we can say the energy decreases by a factor of bubbling 4. The energy changes by 1 over 4. If you say energy decreases, then you just have to say by 4 times. But if you just say energy changed by a factor, then you have to say 1 over 4. And I believe you already know that. But the next thing that we have, Basha. Now, we had a question that says, for the energy, right? For the energy increase 5 times, by what factor should the amplitude change, right? Or it could be anything else actually, right? Or let's make it 3. For the energy, all right, for the energy to increase, Babylon, to change, to become 3 times, Basha, by what factor should the amplitude change? So how do we do this one now? So because most of the question, like I said, gives you the amplitude, you just find the energy. But what if they gave you energy and then ask you for the amplitude change? By what factor should the amplitude change in that case? Yalla Baba Gutman, all you have to do, just write the equation, right? It is directly proportional to the amplitude squared. That's now for the energy to become 3 times here. So this is, we can say, it is directly proportional to this one, yeah? So we can say amplitude squared, but we want the amplitude, not the square. So in this case, you'll take the square root for both sides in here, this to cancel out. So the amplitude needs to change by square root of 3, then the energy increases 3 times. And if you want to, for example, use a number, then you'll just find the square root of 3, which is going to be 0 point something, right? Okay, what is the square root of 3? It is, 1 point something, 1.73 here. So this is how much the amplitude should change in order for the energy to increase 3 times there. And I need you to be careful with this one. So, and of course, this relation would answer anything here. And this is, of course, the relation, and these are some examples for you to practice as well. So, good man, if the amplitude double, energy could be to 4 times more. If it is halved, it becomes what? 1 over decreases by a factor of 4. And then, but if the amplitude doubles, all right, then we can see that the energy, or if the energy doubles, the amplitude must change by the square root of 2 in that case. All right, and this study tip talks about this one. If the energy is given, to find the amplitude, use the square root of the energy. Just use the equation, and then you can find that amplitude. Good man, this is the main relation. If you want to find the amplitude, take the square root for both sides. Data cancel the b, so amplitude is equal to this much. But there is one thing you need to know, Baba. When it comes to a mass spring system here, a mass spring system, if you remember, like here is a mass spring system that oscillates when you're back and forth, back and forth. So we were assuming that if no energy is lost, then this pendulum keeps oscillating up and down. So this will be the amplitude of every oscillation forever, yeah? But we know that this does not happen in real life, yeah? Because remember, we said amplitude is directly proportional to the, the energy is directly proportional to the amplitude square here. So if no energy is lost, this is how the wave looks like, and this is the wave that we draw. But what does it happen exactly in real life, Baba? We know that as the wave is oscillating, eventually it's going to stop, yeah? But what happens before stop? This oscillation becomes less and less, until it, for example, completely stops at this point here. But as first it is going to oscillate back and forth at a large amplitude way. It becomes smaller and smaller and smaller until it completely stops, right? This is how. So if we draw this one, this is how it looks like in reality, all right? Until it eventually stops in here. So this indicates that there is an energy loss in here. So what do we call this one in physics, Baba? As the energy decreases until it becomes 0 or approaches 0, we call this process damping. Basha? So damping, it is when the energy of a system, let's say, it decreases until it approaches 0 or it becomes 0. Basha, this is what happened in real life because of friction and air resistance. But all the cases that we study, we consider the situation as ideal, so we assume no energy is lost. Again, if no energy is lost, then this is how the wave looks like. So you can call this one an ideal wave. All right. So here in a mass spring system or simple pendulum, could be even that, the amplitude of a wave gradually diminishes, decreases, gets smaller over some time, Basha. So in that case, of course, we can see that over the time energy is dissipated. Dissipated, that means it is lost, by the way. This effect, it is called damping. Okay, now another question that we have says, what is one advantage of transferring energy by electromagnetic waves this time? Now we know that electromagnetic waves have the ability to transfer a large amount of energy, Basha. They can do that very quickly too because they have the speed of light. I hope Sarishman here, it is related to the question that where the amplitude energy relation. It says, when the amplitude of a mechanical wave is tripled it's 3 times, yeah? The energy of a wave, all right, carries in a given time interval, it is increased by what factor? With money relation, okay, try to write it down, so that is amplitude squared, Basha. Amplitude, okay, it is changed by 3 times, so 3 squared, not cubic, 3 squared, that would be what? That would be 9 times. So we can say that the energy increases 9 times. and that'll be C. Now, section review here says what? As a wave passes by a duck floating on a lake, Basha. So consider there is a duck. Right? Here's water waves, and there is a duck. Could be a piece of wood, could be a duck, could be anything, right? All right. Consider this as a duck. Okay, so what do you think will happen as the waves are passing? The duck moves up and down, or you can call it bob up and down, which means it is moving up and down, right, out of this position without moving forward or backward. Basha? Well, so the question says, but remains essentially in one place, the duck. Why doesn't the wave carry the duck along the direction of the propagation? Previously, we said that. We said the waves normally pass through the medium, right? They only make mechanical wave. They only make the particles of a medium to vibrate, but they do not transfer the particles of the medium, or they do not take the particles of the medium with them. So once again, the waves only make the particles vibrate. They do not carry the particles of the medium with them. If that was the case, then there shouldn't be any water waves left in the ocean, because they would have been all moving with the water waves. Or when you talk to somebody, there shouldn't be any air left for you to talk anymore, because the air particles would already have left. But these are not the case, we know that. All right, so the disturbance move, not the medium. Now this one here, these questions says, sketch each of the following wave that appear on the string here. Of course, in Wizari, they won't ask you to sketch, but they might give you some sketches and say which one of them is this or that. So the first one says, sketch a pulse wave that is a longitudinal. And remember this, Baba, longitudinal is like a spring one, yeah? And it is a pulse, not like a full wave. So if we have a spring here, okay, this is a spring. If you just give it one push forward here, that is going to be like just one push forward and then back to the same point, right? So what is one full wave? Let me tell you. You have to push forward and then back to here and then go to the other side and then back to the same point. That would be one full wave. But if it is just a push forward and then back to the same point, that is going to be a pulse, and this pulse would be moving along the direction of a spring. That is a longitudinal pulse. That would be a longitudinal pulse. And the reason why we call it a pulse wave, because it is a wave carrying only a single pulse. Now another example, or the second part says, a periodic wave that is longitudinal. A periodic wave this time. If it is a periodic wave now, you can keep, like giving or making this spring go back and forth, and then the pulse, of course, would be moving back and forth. So these pulses or the waves would be moving forward. When we say periodic, and it keeps repeating or happening over and over at regular time intervals. Basha, that is for this. What about for C here? C says, okay, periodic wave, there's, okay. C says a pulse wave that is a transverse. Once again, the other time we said it, the other lesson, and if you have a rope that is attached to something, Baba, if you just move it up and then back to the same point, then it would only generate a pulse upward. You could do that the same if you want to have a downward pulse, Basha. That is a single pulse that is traveling here. But the part D says a periodic wave that is transverse. Now, if it is a periodic wave that is transverse, a full wave, let's say, then in this case, you can move the whole thing up and then back down to the equilibrium and then move down and then go back to the same point. So that is going to be all the way up and then back down and then back to the equilibrium. So this one is going to generate one full wave in here. But since it says periodic, so you keep doing that up and down. So there will be pulses moving on this rope, string, spring, whatever that you're using to produce the waves with. That is part D. A periodic wave that is transverse, that is going to be this one. Now, question 3, which I think it is the most important question here, says draw a graph for each of the waves described in B and D for questions 2 and label y-axis of each graph with the appropriate variables labeled following on each graph, crest trough, wavelength, and amplitude, and all that. Basha, if we, for example, the first one that we have, right, using a graph for each of the waves mentioned there, all right, but if we're going to use this one, Baba, but man, for the longitudinal wave, if we're going to use a periodic or a sine wave for that, good man, instead of every crest, we can write a compression here, one, yeah? All right, and then this would be a rarefaction for that, and this would be the amplitude here. But this side, the most important thing here, Baba, if it is a sound wave or longitudinal wave that we're going to draw as a sine wave, at y-axis, it must be written maximum pressure or density. And then here, if this is maximum, of course, the lower side would be minimum here. But on the other side, or on the other hand here, if this is a transverse wave, we have crest, trough, and then amplitude. That would be the maximum displacement from equilibrium position here. And then this side must be written displacement. So whenever you're given a diagram like this, a sine wave, before you say it is a transverse wave, always look at the y-axis. If it is written pressure density, that is a longitudinal or belongs to a longitudinal wave. If it is written displacement, that is a normal transverse wave. That'll be the end for this session. Inshallah, next session, we're going to start with wave interaction. That is also an interesting topic. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.